This is our formal lab on finding the charges of balloons. The main problem that this lab works to address is how we can find the charges of two objects. Our main punchline is that we weighed each balloon separately and charged them up using a specific method. We then placed one balloon on a scale and observed how the weight value changed as the second balloon approached it. Our motivation for conducting this experiment is that finding the charge of a specific object can implicate its use in other scientific areas such as engineering and medicine. Our experimental findings were the specific charges of the balloons, that the balloons in trials 1 and 2 attracted and the balloons in trial 3 repelled. Here is the outline of our experimental procedure. We blew up two balloons to relatively equal masses, balloon 1 being 2.65 grams and balloon 2 being 2.56 grams. We rubbed both balloons on a sweater for about 10 seconds. Balloon 1 was placed on a scale, while balloon 2 was held at a constant distance above the scale, which was about 80 centimeters. We moved balloon 2 towards balloon 1 by hand at approximately 3 centimeters per second. We recorded the change in weight of balloon 1 as balloon 2 approached but did not touch balloon 1. The trial ceased just before the balloons made contact with one another, and 3 trials were conducted. Here's our experimental limitations. First, the balloons may not have been charged for the same amount of time within and between trials. This could cause a difference in the calculated charges of the balloons across trials. Additionally, the balloons were left to idle for different periods of time across trials due to inconsistency with starting each trial. This could cause the charges to deteriorate over time and produce inconsistent calculated charges. Also, if balloon 2 didn't start at the same height across all trials, that could cause premature weight changes early in the trial, affecting the calculated weight change and therefore the charges. Finally, the angle of the camera made it hard to measure the distance between the balloons accurately. Some ways we tried to minimize error is that we charged up the balloons for an equal amount of time for each trial. We kept balloon 1 and 2 rolled the same for consistency, and we conducted 3 trials.
So for our experimental expectations, our main focus was using the electrical force, which is Kc times Q1 and Q2, which are the charges of balloon 1 and balloon 2, and R squared being the distance, and R hat, which in this case was 1 due to being in vertical motion. So here we have the energy pie charts. So we have two situations of repulsion and attraction. When the balloons are repelling each other, the electric potential is positive and becomes more positive, and the kinetic energy decreases as the both balloons get closer. And for attraction, the potential energy becomes more and more negative as both balloons come closer, and kinetic energy also increases. For our free body diagrams, the chart, the main force on balloon 2, which is fixed, was force of gravity, and how when that changed, that's how much of the electric force that was acted, equal and opposite on both balloons. And this is our system schema with our two balloons and the scale and the Earth. So this is our data for each trial, and we collected at 3 centimeters, 2 centimeters, and 1 centimeter for each one, and calculate the change in mass. So here we graphed our data using the change in mass of the force gravity, which is the amount of electric force that is acted on balloon 2 and balloon 1, and then compared how much it changed as the balloon got progressively closer.
Okay, so for our trial 1 results, the way we analyzed the data was at each distance, we calculated the amount of weight and change in the fixed balloon, and then we multiplied that by gravity to get the force in newtons. And then once we got the force, we plugged that back into the equation for electrical force, and for each distance, and we got the Q value. And once we got the Q values, I took I added all of the 3 Q values up, and then I divided them by 3 to find the average charge that the balloons were experiencing with each other. And then I did the exact same thing for trials 2 and 3. So conclusion, trials 1 and 2, since the weight on the scale was a negative, the approaching balloon was opposite in charge to the balloon that was on the scale. And for trial 3, since the weight on the scale increased, that means the approaching balloon was the same charge as the balloon on the scale. And to answer our original question of what charges the balloons were, the charge of the balloons in trial 1 were negative 1.52 times 10 to the negative 7, The charge of balloons in trial 2 were negative 1.13 times 10 to the negative 7, and the charge of balloons in trial 3 were 2.31 times 10 to the negative 7 coulombs.